The next is the long form of the periodic table, which is also known as the modern periodic table. Now this modern periodic table was given by Moseley, and currently we are following or we are using the same periodic table. This periodic table have the total 118 places. That means this periodic table can accommodate total 118 elements. In the case of this modern periodic table, all the elements are arranged in the increasing order of their atomic number. So here elements are arranged in increasing order of atomic number. So whatever the elements we have, they all are arranged in the increasing order of their atomic number, and hence we have a modern periodic law, the law for the periodic law for this modern periodic table. And the law is that all the physical and chemical properties of the element is a periodic function of their atomic number. In case of modern periodic table, the law was that periodic function of atomic masses, while here the properties are periodic function of their atomic number, because here the arrangement has been done on the basis of atomic number only. Now this is a modern periodic law, modern periodic table I can say. This periodic table contains total 7 periods. The number 1, 2, 3, 4, 5, 6 and 7. So these are the 7 periods. The first period is considered as the shortest period, which is containing only 2 elements, that is those 2 elements are hydrogen and helium. The next period, second and third, is considered as the second and third, these 2 periods are considered as a long period, short period as they are containing 8 elements. That is, the first period contains only 2 elements. The second and third period, as I said, they are called as short period, which contains 8 elements. The fourth and fifth period, they contain total 18 elements. Each of them contain 18 elements. That is the fourth and fifth, and that's why they are called as long period. And sixth and seventh period, they contains 32 elements. Each of them contain 32 elements. Now in case of 6 and 7, here we have 18 elements. These two are called as Lanthanide series and Actinoid series. Out of this, first one is called Lanthanide series, and the second series is known as Actinoid series. So this lanthanide and actinoid, they are placed here in a group number 3. Here we have lanthanum and here we have actinum. So whole lanthanide series is kept in the lanthanum. This means this single column is containing total 15 elements. The one is a lanthanum and the next is these 14, that is from cerium to lutetium. Then actinoid series, this contain all the elements from here to here. Okay, so this 6 and 7 is containing total 32 elements, that is, they are considered as longest period of the periodic table. Now it has been observed that elements belonging to the same period contains the same number of shells, or here the number of period represent the number of shells. For example, suppose I am saying if there is any element present in period number 3, or I can say all 8 elements which are present in period number 3, they all are having same number of shells, that is 3 shells they have. Element present in 5th period, there are total 18 elements present in a 5th period and they all are having total 5 shells, that is outermost shell for them is 5. Element present in a 7th period, they all are having 7 shells. So here the number of period represent the number of shells. After that, so as I said, there are 7 horizontal lines and those 7 horizontal lines are called as a period. Now let's talk about the group. Here we have total 18 groups. When the periodic table was met, that time we consider that there are total 8 groups, 1 to 8. That time it was considered there are 8 groups, 1 to 8, and all the groups were divided into 2 parts, that is A and B part. Means first A, second A, third A, fourth A, similarly first B, second B, third B. It was considered, but so initially the groups were numbered in like first A, second A, like that, but then IUPAC changed this numbering, and IUPAC numbered is simply from number 1 to number 18. So group number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 up to 18. Now here the group number 1 and the group number 2, they are highly alkaline in highly metallic in nature, and as you move from here to here, that metallic nature goes on decreasing and the non-metallic nature goes on increasing. And in this case, the second last group, that is called as a halogens, they are highly non-metallic. Group number last, that is this group, is called as a zero group. As I said, these two, group number 1 and group number 2. So group number 1 is called as alkali metals. Group number 2 is called as alkaline earth metal. Alkali metals, that is these are the metals whose hydroxide or oxides are when dissolved in water, they produces a basis, that is a alkali, that's why they are called as alkali metal. Alkaline earth metal, the name is the reason is same, that is when the oxide or hydroxides of these two group 2 element is dissolved in water, again produces alkali, but since we get it from the earth crust, that's why the name is given alkaline earth metal. Then group number 18 we have. Group number 18, it is known as noble gases or inert gas. This group number 18 is also known as a zero group, that is a zero group elements, that is a noble gases, because they have the valency as a 0. And then group number 18, before that we have group number 17, which are called as halogens. So these are the some famous group I can say, which have the some specific name. So we have group number 17, that is called as a halogens. Halogens, the alkali metals are highly metallic in nature, while the group number 17, that is halogens, are highly non-metallic in nature. And as I said, when you are moving from left to right in a periodic table, your metallic property goes on decreasing and the non-metallic property goes on continuously increasing. After that, from group number 170, here we have this then group number now in the case of this periodic table, this group number from all the elements which are present in a same group, they have the same property. That is, for example, the group number 1, the elements present in this group number 1 is lithium, sodium, potassium, rubidium, cesium, francium. They have the same property except hydrogen. Hydrogen possesses the properties of both metal and non-metal. The hydrogen, this is the one of the limitation of the periodic table, that is modern periodic table, that in this the hydrogen is not kept at a proper, means there is a no fixed position for the hydrogen. Hydrogen is currently kept with the alkali metal, that is group number 1. But the problem with hydrogen is that the hydrogen shows the properties of alkali metal, that is group number 1 metal elements, as well as shows the properties of the halogens. So somewhere where to keep it, whether hydrogen should be kept with the group number 1 or it should be kept with the group number 17 is always a question mark. But on the basis of its electronic configuration is kept here. So except hydrogen, if I'm considering other element, lithium, sodium, potassium, rubidium, cesium and francium, they all are belonging to the same group, and that's why they have same property. All the element belongs to this group, they have same property. Then here we had the whole periodic table has been classified into 4 blocks. We have total 4 blocks here. Those 4 blocks are named as S block, P block, D block and F block. All the blocks are always represented by the small letter. So small letter S, small letter P, small letter D and F. Now the first group. Now here the classification has been done in 4 blocks on the basis of, I can say, electronic configuration. Now S block is assigned only with the 2 groups. The first 2 groups are called as S block. Why only 2 groups? Then simply I will say because the S orbital, these names are given on the basis of the name of orbitals. When we write a electronic configuration, then while writing electronic configuration, we mention like 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. So over there, the orbitals are named as sp, df, and on the basis of those orbitals names, we are having 4 blocks, that is sp, d and f block. S block, as I said, S block is given with only 2 groups. That is group number 1 and group number 2. Then answer is that S block is given only with the two groups. The reason because the capacity of S orbital is, or S orbital can accommodate maximum 2 electron. That's why here they are having two groups. P block. In the case of this, here the P block is assigned with the 6th group. Group number 1 and 2 comes to S block. P block, it is from group number 13 to group number 18. That means total 6 groups are assigned to the P block. Why 6 groups are assigned to the P block? Then simply I will say the P orbital. The capacity of P orbital is of 6 electron. P orbital can accommodate 6 electron. That's why in periodic table they are provided with 6 groups. Then D. The capacity of D orbital is of accommodating 10 electron, and that's why here the D block is assigned with the 10 groups. So D block, it is assigned with the 10 groups, and those groups are group number 3 to group number 12, which is placed between the S block element and the S block element and the P block element. Then F. The F block element, as I said, this belongs to group number 3 and period number 6. Period number 6 and 7 means they all are belonging to this, but at the same time when it is written on the downside of the periodic table separately, then you can say that they are given with each series is containing 14 elements. So while F block elements are containing 14 element series, the simple reason because F orbital capacity is of 14 electrons. Okay, now S block element, and this is, as I said, it is a P block element. This S block element and P block elements, they are simply known as normal element, or also known as representative element. So they are normal element or also known as representative elements. The name is given normal element or representative elements because in case of S block and P block, only outermost shell is empty. So the reason only outer valence shell is incomplete. While in case of D block element, which are from group number 3 to group number 12, that is from here to here, this is D block. These D block elements are also have a name that is called as transition element. So they are transition element. Transition element because their last two shells are incomplete. Last two shells are incomplete. The outermost shell is called, the last two shell, that is outermost shell and the second last shell. Outermost shell is called as a valence shell, while the second last shell is called as penultimate shell. What second last shell is known as penultimate shell. And if I am talking about the third last shell that is a before the penultimate shell, so it is called as pre-penultimate shell. So outermost shell, we called it as a valence. Second last shell is called as a penultimate shell, and the pre-penultimate shell, that is third last shell. Now F block element. F block element, that is from group number 3, period number 6 and 7, that is these two series, Lanthanide series. They are F block. So they are F block element which are known as inner transition element. Inner transition elements. The reason calling it as an inner transition element is that their last three shells are incomplete. So the last three shells are incomplete. Last three shells means which three shells? I can say the valence shell, outermost, penultimate shell, that is second last shell, and pre-penultimate shell, that is the third last shell. So these three shells are incomplete in case of F block element. D block elements are called as a transition element. So reason of calling it as a transition, there is one more reason for calling it as a transition element, is that the meaning of transition is a change. So as I said here on the extreme left hand side, the elements present, whatever the elements are present, they are highly metallic in nature. But as you move toward the extreme right, that is in the case of this, there is a highly non-metallic nature. That means ultimately I can say that metallic property slowly goes on decreasing, and that metallic property is decreasing and non-metallic property is increasing. So that certain change is taking place, and that change is taking place across D block element. That's why it is called as transition element, because that metallic property slowly decreases, that is changes. So as I said, we have 4 blocks, S, P, D and F. S block elements, they have general electronic configuration NS1 to 2. P block elements have the general electronic configuration NP1 to 6. And D block elements, they have a configuration like, or I can say here it is NS2 NP1 to 6 valential configuration. D block element, their last 2 shells are incomplete. And S block elements, that is the element whose last electron enters in S orbital, that's why the last electron enters in S. P block elements whose last electron enters in P orbital, that's why P. D block whose last electron enters in D orbital. But when the electron enters in a D orbital, then that D orbital is never from the outermost shell, but from the penultimate shell. It means the D block element, they start from the period number 4. And if they are starting from the period number 4, that is the valence shell is equal to 4th period. 4th will be the valence shell. But electron will never enter into the 4th shell of the D orbital of a 4th shell. Instead, the electron will enter in the D orbital of penultimate shell. So if the 4th shell is outermost shell, then penultimate shell will be 3rd shell. That means if the electron is D block element, as I said, the element whose last electron enters in D orbital of penultimate shell. So whenever the electron will fill, it will fill in 3D. I'm talking about those elements which are present in 4th series, that is here, 4th period. And that's why the 4th period elements, D block elements, are also known as 3D series element. 3D series element because whatever the elements here we have, their last electrons enter in 3D orbital. So this have a general configuration NS2 and then N-1 D 1 to 10. NS2 N stand for the outermost shell. So if I'm considering the element present in 4th shell, 4th period, any D block element, for example scandium here we have. So configuration for scandium we have atomic number is 21. It's a 4s2 3d1. So NH2 N-1, that is 4-1 D1. Here we have titanium, the configuration is 4s2 3d2. Here we have zinc, it is configuration is 4s2 3d10. That means it is 4s2 and 3d will change from 1 to 10. Similarly, if it is 5th period, then configuration will be 5s2 4d1, like that. Then F block element. Group 3, whose last 3 shells are incomplete. F block elements are those elements whose last electron enters in F orbital. This is the definition of F block, that is whose last electron. Means if I am having an element and its last electron entering in F orbital, then I will say that that particular element is a inner transition element, that is a group F block element. So again, if the electron is entering into the F orbital, then it is always not from the outermost shell. It is from the pre-penultimate shell. Pre-penultimate shell, for example, the F block elements are kept here in period number 6 and period number 7. So let I'm talking about the element which is in period number 6. So if the element is in period number 6, then for that valence shell will be 6, then penultimate shell will be 5, and pre-penultimate shell will be 4. Means the element whatever we have in Lanthanide series, their last electron enters in F orbital of pre-penultimate shell. That means the last electron enters in 4f orbital. In which 4f orbital. The general configuration for the F block element is NS2 N-1 D. Sometime it is 0 or sometime it is 1. Sometime D orbital takes 1 electron from the F orbital to get the empty or half filled or completely filled stability. And then N-2 F 1 to 14. N- where N stand for the outermost shell. So if the outermost shell is a 6th, then F orbital will have an electron, then N-2, that is 6 2, 4f orbital. Actinoid series, it is 7s, outermost shell is a 7 because it belongs to 7th period, and D will be from 6D and electron will enters into 5F. So lanthanide series is also known as 4F series element. They are called as 4F series element because their last electron enters in 4F orbital, and actinoid series elements are called as 5F series element because the electron enters in 5F series. Now in the case of this, as I said, S block element, they have two groups and the configuration is NS1 to 2. So here I can say this is NS1 and this is NS2. Means in case of S block, I can say if any element is S block, and if its last electron enters as a S1 or S2, if it is S1, it will belongs to this group, and if it is S2, then it will belongs to this group. So this is about the modern periodic table, which we had already studied in last. Some part of this is already done in the previous standard. Okay, so this is about the modern periodic table.